Hi all, welcome to lecture 14 of this lecture series named Unconstrained Optimization, and today's lecture is on classical Newton method. So in today's lecture we'll try to learn about this very popular optimization algorithm known as Newton method. We'll try to know about its motivation, how did it originate. We also will take a look at some examples, how is it better than steepest descent method. We'll also look at its pros and also cons of these algorithm in today's lecture. So let's start the lecture. Now before starting the lecture, let's just recall what we studied in our previous lecture. So we first of all we studied what is a steepest descent method. So in a steepest descent method, let this be uh, a contour map of a function that we want to optimize. Let this be the current point xk, and let this be the gradient of the function at xk. Alright, so in steepest descent method, what we do is we approximate the function to a linear function around this region, around a small region around xk. We approximate it linearly, and then we try to find the direction in which that linear function is maximally reduces. So the reduction is the maximum, and that direction comes out to be the opposite direction of the gradient function, that is minus of gk. So first, steepest descent method, and the direction of descent direction is chosen to be opposite direction of gradient, that is minus gk. There were some points that we observation that we got with the steepest descent method, that if we have circular contours uh, it takes one step to reach the minimum. For steepest descent, if we are using exact line search, that is given. So if we use exact line search and we have circular contours and we use steepest descent method, we'll reach whatever initial point you choose, you'll reach the minimum in one step. But if the contours are elliptical, it takes a lot of steps. And also it takes different steps from different initial positions. So maybe from some initial position you might converge to the minimum in less number of steps, while on the other hand, if you take a different point on an elliptical contour, you will take a lot of steps. So that was the problem with the steepest descent method. So given these observations, we asked ourselves a question: can we transform the elliptical contours to circular? Elliptical contours to circular contours. To get a solution in one step. Can we do that? So can we take it? So let's say we have a quadratic function which has elliptical contours. We transform it to circular, and now that it is circular, we'll get the solution in one step, right? Can we do that? So it turns out we can do that, and we also formulated a way how to do it. So let me just do it here for you. I'll just make a diagram of elliptical contours. Alright, so let me just draw the axis. Alright, so this is our elliptical contours. We can transform it, let's say, for simplicity, the function is given by half x transpose hx. It be given by this. So if we transform it like this, let y equal to L transpose x, which gives us x is equal to L inverse transpose y. If we transpose is like this, where L is a Cholesky decomposition lower triangular matrix of H. Okay, so this will become half of y transpose L inverse L transpose L inverse transpose y. So you can see these are inverses, and this becomes half y transpose y, which has circular contours. So this particular function has circular contours in the transformed domain. I'll just draw it. Okay, all right. Okay, so this we have circular contours, and here we can say that h y equal to half y transpose y. So given this transformation of given this transformation of the space or the coordinates, what was the update step for our optimization algorithm for steepest descent? Xk plus 1 gives us xk minus h inverse gradient of f xk. Here step length is 1, so alpha k is 1. We have assumed that. So you can see that we have a second order information requirement here, h inverse. So which changes the direction of the steepest descent. So it rotates the steepest descent direction a little bit. Now this is one of the motivations that I told you, but it turns out that let me give you a fun fact that this is not the real motive. So it turns out this method, some of you might know, multiplying h inverse or the Hessian inverse to the gradient is actually what we do in Newton's method. So this is a Newton method, basically what Newton method is. But this is not the way we came to this formula, is not the real motivation for Newton's method, because the Newton method was invented or was developed in 17th century. So Newton method was developed in 17th century, while steepest descent method was developed in 19th century. So actually by Cauchy. So actually, the way we came up with this Newton method, that we started with steepest descent and then came to the Newton method. It's not the real motivation behind it, because Newton's method came around 200 years ago then, from steepest descent method. So it's not the true inspiration or motivation behind the Newton's method. So not the true inspiration behind Newton's method. So it's a good way of thinking about Newton's method. So it's just you can derive it from steepest descent. This is a good way, or a different way to look at classical Newton's method. Now let us look at the real motivation behind the Newton's method. So let's look at that. So motivation behind Newton's method. So what could be the motivation? So let's say we have a minimization function which is continuously differentiable, and we want to minimize it over whole of Rn. So this is the problem, let's say. Now let us make a graph of this function. It may not be quadratic or anything, it can be a general function. We'll assume that it is bounded below so that its minimum is possible. So let's say this is the function. All right. So the motivation behind finding the minimum problem is, let's say I start with some point here, xk. All right. So what I do is I approximate this function to be a quadratic function here. All right. I approximate this function to be a quadratic function through expansion, through what you call Taylor series expansion. We assume it and then find its minimum. So it will, because it's quadratic, it will always have a local minimum. We use this as the next point, xk plus 1. We see where does it cut the original graph. We assume quadratic function again, find its minimum, and this is how it goes on. And the idea is that it somehow reaches the local minimum. You can see it eventually it will come to the local minimum. All right. So yeah. So this is the motivation behind Newton's method. We can also look at it in contour maps. So this was just a single variable graph. So let's look at some contour map which will help us see what this the motivation of classical Newton's method. All right, this. All right, so let's say this is the contour map of a function. Okay, and now let's say this is my initial point xk, or some iteration point xk. What I do is I approximate it to be a quadratic function around this point. All right, so this might be a quadratic function approximation here. Now in Newton's method, what I find its smallest point. So let's say this will be the local minimum of the point of this function, new approximated function, and I use this as xk plus 1, and then this goes on. All right, so this is the idea behind classical Newton method. Let's also look at it in one more way. So we know that we saw earlier that and the descent direction can be anything from minus ak gk. All right, minus ak gk. All right, so in steepest descent, this ak is I. All right, this ak is I. So this descent direction becomes minus gk. For Newton's method, which we are looking now, this direction becomes minus hk inverse. All right, so the descent direction becomes hk inverse. All right, so this is the difference between this is the motivation behind classical Newton method. So we take a point, we approximate it to be a quadratic function using Taylor series around that point, find that quadratic function's minimum point using this method, and because it's a quadratic function, this will give us the minimum in just one step. We use that as a current point and then keep on doing this unless and until we reach the local minima or the stationary point of the given function as of the given minimizing function. So this is the motivation behind the Newton's method. Now let's look now let's look formally to the formally at the Newton's method. So let's discuss Newton's method formally. So let's consider the problem of minimizing over x belonging to Rn fx. So we want to minimize fx where f belongs to continuously differentiable function set. Basically it is both continuous, differentiable, and its first differentiation is also differentiable, so we can go to second derivative information, and f is bounded below. All right, so these are the assumptions. So in Newton's method, as we discussed earlier, we use second order information to find the descent direction. Use second order information to find a descent direction. All right. At every iteration, we use Taylor series to approximate f at xk by a quadratic function. And find the minimum of this function, and find its minimum to get xk plus 1. Alright, so what we do is we approximate fxk to a quadratic function fqxk, which is given by fxk plus gk transpose x minus xk plus half x minus xk transpose hk x minus xk. So this is the quadratic function approximation of fx around xk. We try to find the minimum of this function. So how? Let me just put it in one frame. So yeah, so how do I find the minimum of this? So I'll find the minimum of this function. So xk plus 1 is nothing but argmin over x of fqx. Okay, so for minimum, because it's a quadratic function, the minimum will occur at where the gradient is 0. So delta of fqkx is equal to 0 implies that this gives us xk plus 1 is equal to xk minus hk inverse g of k. So here we are assuming hk is invertible. So we are assuming that. So we can see that xk plus 1 is equal to xk minus hk inverse gk is of the form xk plus 1 equals xk plus alpha k dk. Right, here alpha k is 1 here considered. So this is called classical Newton algorithm. So in classical Newton algorithm, Newton direction, the direction is given as minus of hk inverse g of k, and step length is given as 1 unit step length. Alright, so this is the classical Newton method. So we might have some questions related to this method. So first question that naturally comes to mind is the direction that we are looking, the Newton direction. Is it a descent direction? So the question that first comes to my mind is d and k are descent direction. So remember, descent direction is descent direction is a direction which belongs to a descent direction set, and descent direction set is given by which makes an obtuse angle with the gradient. So if gk transpose dnk is less than 0, then it's a descent direction. So what is this equal to? Gk transpose hk inverse gk minus. So this is less than 0 if hk inverse is positive definite or hk is positive definite. Right. So if hk is positive definite, hk inverse is also positive definite, and hence this is greater than 0, this quantity, and this whole quantity, because it has a negative sign, is less than 0. So which gives us the conclusion that d and k is a descent direction if h of k is positive definite. Alright, so this is the answer to that question. Now let's look at what does this classical Newton algorithm does to a quadratic function that we saw earlier. So consider the problem to minimize. Fx is equal to half x transpose hx c transpose x. We already have some idea what will happen. So as we saw in that transformation case, it will give us solution in one step if we use exact line search. So let's try to derive that or see it formally or mathematically. So if it is a quadratic function, H is symmetric positive definite matrix. Okay, so S dot P dot D dot SPD means symmetric positive definite, and for it to be to find its minimum, the gradient needs to be 0, which gives us the minimum to be H inverse C. Alright, it's a strict local minimum. How did we get this? So Gx is given by Hx minus C equals 0, which means X star equal to H inverse C. Alright, this is how we got this value. Now if we, this is the local minimum. Now if we apply Newton's method, starting with some initial point x0. So let's say we apply Newton's method. To this quadratic function. Be any point. So it's not that we are taking any specific point, it can be any point in the domain. And G, what is G of x naught? It will be Hx naught minus C. Alright, so what is the initial descent direction? Minus H inverse H x naught minus C. Okay, so this gives us minus x naught plus H inverse C, right? And alpha naught is equal to 1, right? So what will be x1? Is x naught plus alpha naught dn naught, which will be given by x naught plus minus x naught plus H inverse C, which gives us H inverse C, which is actually the strict local minimum, as we saw here. Right? So whatever point you choose, you'll get through classical Newton method. If you have a quadratic function, you'll attain the minimum in just one iteration. That's the power of classical Newton method. So let's just write this observation using classical Newton method. The minimum of strictly convex quadratic functions with invertible Hessian matrix is attained in one iteration. is attained in one iteration. From any starting point. Alright, so this is the power of Newton's algorithm, that for a quadratic function whose Hessian matrix is invertible, a convex quadratic function, strict convex quadratic function which Hessian matrix is invertible, will take us to the optimal point in one iteration starting from any point. So let's look at the classical Newton method in algorithmic form. How can we write it in the form of algorithm? So classical Newton algorithm. All right. So first thing is initialize, as there always is. All right. So initialize x naught and epsilon and set k equal to 0, the iterate equal to 0, right? Then we start the loop while the stopping condition is satisfied, that is, as we have already discussed earlier, the gradient's norm should, if it is greater than some value epsilon, some small value epsilon, we will continue the loop. And the first step is, what is the descent direction? So descent direction is given by hk inverse minus hk inverse gk. We set the step length also, alpha k equal to 1. Then we update the value of x, and we also update the iterate, and we end the loop. So it looks very simple, but the catch is we need to somehow calculate hk, which is actually a difficult part of this algorithm, which we'll look at it later. And now the output is x star is equal to xk, which is the stationary point of fx. Alright, so this is the algorithmic form of classical Newton algorithm. Now we'll look at some examples which will help us appreciate the power of Newton's algorithm. So yeah, let's look at them. So example 1, minimize fx defined as 4x1 square plus x2 square minus 2x1 x2. Right, so this is a quadratic function. So let's just draw the contour map of the function. All right, so all right. Okay, so this is, let this be the contour map of the function, and because it's a quadratic function and we are using classical Newton algorithm, if we start from any point, let's say this be x naught, we'll reach the minimum in just one step, in just one iteration step. Or you may want to take you may want to take some another point, start with some other point. Even from here you will like converge to the minimum in absolute one iteration step. So this is the power of a classical Newton method, that classical Newton algorithm applied to fx converges to x star in one iteration. From any starting point. Okay. But one of the negative aspects of this classical Newton algorithm is that classical Newton algorithm method needs the second order information. Order information which might be difficult to get. Alright. So we saw the usefulness of Newton's algorithm on a quadratic function. Now let's see it on a function which is non-quadratic. Okay, so let's look at some example. Let's look at Rosenbrock function. So what is Rosenbrock function? Let's define it first. So minimization of fx, where fx is defined as 100 times x2 minus x1 whole square, x1 square plus 1 minus x1 whole square. So it's a Rosenbrock function. So if we apply classical Newton algorithm, with backtracking line search, and we take the initial point to be minus 1.2 comma 1 transpose and we take the step length to be 1. For backtracking algorithm, we take rho to be 0.3 and C1 to be 1 into 10 to the power minus 4. Then this converges in 20 steps. And let's say you take some other x naught to be 0.6 comma 0.6 transpose This converges in 9 steps. Please note the optimal point is 1, 1 here, right? It converges in 9 step. Whereas if you if for minimization of Rosenberg function using steepest descent method, it takes around steps greater than 2000. More than 2000 number of steps are required. So as you can see, there is a drastic decrement in the number of steps required. But there is a catch that but every step of classical Newton algorithm requires large computation time for calculation of H inverse. So here each step requires large calculation time, but here each step requires less time, but the number of steps are less here and more in steepest descent method. So that's the case. For each step, the time required is more in classical Newton, but the number of steps required is less. On the other hand, each step takes lesser time in steepest descent method, but the number of steps are huge. In this particular case, more often than not, the classical Newton algorithm converges faster, because even if the computation required for each step is large, the number of steps required is very small compared to steepest descent method. So yeah, so that this was the example 2. Now let's discuss some observations of classical Newton algorithm. So let me just first copy the algorithm so that we can just have a look at it. So this is the algorithm. Yeah, so this is the algorithm. In this we first get the descent direction by minus hk inverse gk, and the step length is 1. So this is the algorithm. Let's try to point out some observation that we have already made. So first thing is, so it requires O(n) cube computational effort for every iteration. In 2 way. especially because of step 2a. Basically, that is the calculation of HK inverse. So it requires a high computational effort for calculating HK inverse, and also requires O(n) square complexity. Storage space is required. So on the other hand, steepest descent method doesn't have such huge computational or storage requirements. All right. The second problem that this has, this can be combined as a first problem, that storage and computational effort is huge. The second problem that this algorithm has is no guarantee that decay is a descent direction. Right. So if you see, if HK is negative definite, then decay is actually an ascent direction, which is not what we want, and there is no restrictions on what HK can be. So if HK is a negative definite, that decay can be ascent direction, so which fails our purpose. So this algorithm doesn't check if HK is positive definite. Alright, so this algorithm doesn't check if HK is a positive definite matrix or not. One more numerical problem that we face using this algorithm is HK can be very close to singular matrices. Singular matrix means which are very, very difficult, which are non-invertible. So if it is very close to singular matrices, this could lead to various numerical difficulties. So inverse calculation will be very difficult, and we'll get very maybe wrong values of inverse. Okay. Apart from that, there are several other problems as well, like there is no guarantee of d of fk plus 1, fxk plus 1 less than fxk, because there is no line search. There is no line search that we do. Alright, so we do not optimize according to line search, so this is not ensured. And the number of iterations is sensitive to initial points for non-quadratic functions. For quadratic function, it converges in one step, but in non-quadratic functions it is very sensitive to initial point. So number of steps required to uh, finish the optimization um, may be very huge in if you take one point, and maybe very less in other points. So it's very sensitive to initial point. And sometimes it might happen that if the initial point is not correct, the algorithm might diverge also. So we'll look at the one of the examples that we had looked in one of our so we'll look at one of the examples that we have also looked at in one of our previous lectures, in which we'll see this point how is this algorithm sensitive to initial point. All right, so let's take example in single variable. So consider the example so the example is minimization of x belonging to Rn of log e to the power x plus e to the power minus x. All right, and if you can see here, fx is log e to the power x plus e to the power minus x. Gradient is 1 upon e to the power x plus e to the power minus x into e to the power x minus e to the power minus x. So this is the gradient. And if you look at the graph, right, graph of gradient, so if you look at the graph of the gradient, it will be something like this. All right. Yeah. So let's say we take some initial point here, x naught. All right. If we go ahead with the new classical Newton's algorithm, it will converge to this point first. It will then converge to this point. It will keep on coming closer, and at the end it will come to a point where gx is equal to it becomes 0. All right, so that's the thing. Now let's slightly change the initial point. Let me make this smaller. And slightly change the initial point. Okay, so if I take a point farther than what I took initially, what will happen is it will start diverging. So x2 x3 and so on. So it will keep on diverging, and hence it will not converge. So actually this algorithm does not converge, rather it diverges. So classical Newton algorithm does not converge with this initialization, with this. So just to make sure, this is g of x. All right. So with this initialization, so we saw this earlier also when we discussed optimization in single variable. This is what happens. So Newton algorithm has a problem of maybe being sensitive to the initial condition. It may converge faster, slower, or may diverge based on what initial condition you are choosing. So to understand when does a classical Newton algorithm converges, like what initial condition should you choose for the classical Newton algorithm to converge, let's look at something called locally convergent optimization algorithm. So locally convergent optimization algorithms. So what are locally convergent optimization algorithms? So an iterative optimization algorithm, is said to be locally convergent if for each solution x star there exists a delta greater than 0 such that for any initial point x naught belonging to ball of radius delta and centered at x star, the algorithm produces a sequence x. The algorithm produces a sequence xk which converges to x star. So basically what this definition is saying, let's say we have a function. All right. So and for every local minimum there exists a delta such that any point if you choose inside the ball of radius delta centered around x star, it converges to x star. That algorithm, then that kind of algorithm, and this happens for each local minima of that function. A function can have more than one local minimas. So if that happens for all the local minimas, then that algorithm is called locally convergent algorithm. And it turns out that classical Newton algorithm is locally convergent. Which means for any function, if you can, there always is a, uh, if you are using classical Newton algorithm, if you choose the initial point close enough to the the optimal point, then you will eventually converge to that point. So this is one of the results, that classical Newton algorithm is also locally convergent. There is a proof for this results, that how can we say that is locally convergent. We're not going to do the proof of this, we'll just use it as a result now. And we'll see in the next lecture how is this useful, and can we modify the classical Newton algorithm in certain way so that it gets rid of all the problems that we have discussed earlier. So we'll see that in the next lecture. So we'll end the lecture of stating this result, that classical Newton algorithm is locally convergent. Even though we are not going to do the proof of this statement, we'll use this in the next lecture. Till then, thank you.